Sorry. Got it. Minimize that. So screen myself. That works. Okay, shall I begin?
Yeah, so I'll just give a brief introduction. So welcome everyone to this talk. I think it's a fifth talk in this verification seminar series. And it's a pleasure to have Ranjit Jhala with us. Ranjit is a professor at University of California, San Diego. And he works in various aspects of programming languages, including model checking, program analysis, type systems, and he's probably best known for his work in refinement types. And today, Ranjit will be telling us about using refinement types for secure web applications. Over to you, Ranjit.
Okay, thank you, Deepak. This is a real pleasure. Oh, Sanjeeva says he can't hear the audio, by the way. Deepak's audio is low.
Okay,
You
my
jack up
audio
my
is low,
audio.
is it? Okay, but I think as long as Ranjit's
I
is
can hear
okay.
you clearly.
Okay.
Let me okay, it's
Okay,
audible. Okay, it's a great pleasure to be speaking to all of you. So I want to tell you about, I mean, it's a line of work that I've been working on for 10 years or so, but this is one particular project that we've been working on over the past year and a bit. And this is on how to use refinement types to make web applications better. So what kind of web applications am I talking about? I'm referring to, oh gosh, I'm talking about things, the kinds of applications, for example, Zoom that we're using right now. These are essentially three-tier web applications where there's some sort of client, which is how most users interact with the system. And then there's some centralized server, and then there's some database that essentially has the persistent data about the state of the application. For example, if you're using some kind of money giving app like Venmo or PayPal, who you are, who your friends are, what your account is, so on and so forth, right? A history of transactions and so on. We probably all use things like Easy Chair or Hot Crap, when we're working on program committees and so on, right? Now, these kinds of applications are everywhere, right? I mean, we increasingly use them for all kinds of things. They sort of mediate all aspects of our lives. And yet it's kind of well known that they have all sorts of, possible vulnerabilities, and not just possible. I mean, it's a kind of routine thing. I get emails all the time from my university administration. Your social security number, bank account, and whatnot have once again been stolen. You would think everyone has it on the internet by now. Yeah, so there's this organization called OWASP sort of compiles a list of bad things that might happen to web applications. And high on that list are things like sensitive data exposure and broken access control, where essentially the wrong sets of people are somehow able to poke in and get access to data that they're not supposed to have access to. Okay. And the sensitive data exposure is even, I mean, it wasn't even clear who the right set of people were who should have access to this data. Just in the normal course of running, somehow you ended up leaking information to somebody who wasn't really supposed to get that information. Now, why is it that web applications are dodgy? So, of course, there's lots of reasons. It's a complicated social and software engineering problem. But one of the big reasons is not that people who build these applications do not think about security and do not think about how to, prevent these kinds of leaks. They do. But the way they do it is typically the code that enforces the security or even specifies the security is all lumped in to the application code. So for example, this is a snippet from HotCrap, which is a widely used website for, for paper reviewing, right? We submit our papers and program committee reads and writes reviews on HotCrap and so on. It's like Easy Chair. And I don't pick on HotCrap because their code is especially bad. It's not. It's actually very good. I'm only showing you this because it's available. A lot of the code in this domain is hidden. And if you sort of look inside the code for HotCrap, what you'll see is that the code that's doing the checks for example, look here, this user can view this particular review, and is this person a program committee member, and are they assigned that paper? All of that is mixed into what is called, quote unquote, the business logic, the actual implementation. And this makes it very hard to tell what exactly is the policy that we're trying to enforce over here. What even is the security policy? And it's doubly hard to tell if you've got it right, because it's all kind of finely intermingled with the rest of the code. Right? So if you think of these orange lines as the security checks, they're all sprinkled throughout the application, And so we don't really have a clear picture of, does the application enforce a high-level security policy? So instead, our goal in this line of work, in this system called Storm, is to figure out how you can pull that security policy out from the core business logic. So of course, the code will be doing a bunch of checks, but we want some way to separately be able to specify the security policy itself, and then be able to kind of look at that security policy. You should be able to audit it and you should be, yeah, this is kind of what I want to happen. And then we want to be able to verify that the rest of the code correctly enforces that particular security policy, okay? And the reason we want to do this is that these policies should be much, much smaller than the application code. I don't want you to have to understand the thousands of lines of the application in order to know whether or not your code is good or bad. I just want you to be able to trust and audit this tiny, much smaller policy code. And we're going to do this building via what I call Storm, which is a security typed ORM. Now, security is kind of a vague word, and I'll explain what we mean here. Typed, I'm hoping people are familiar with, but we'll sort of explain it as we go. ORM is this term from the database community, which describes, essentially it's a fancy word for a library that you use in software, in Java or Haskell or ML or whatever, to talk to a database, which typically only understands SQL, right? So ORM is essentially this mapping between a database, a relational database, and a programming language. And we'll sort of see what this looks like in just a second. Okay, so here's what our system sort of looks like. Here's what a web app looks like. You have a central sort of web server, and you have your client, right? This is how you and I interact with a particular web application. And the client talks to the server with an HTTP sort of, over an HTTP session, sending requests and responses up the internet. But the web server also talks to a database. The web server is essentially just, a persistent program, but it doesn't have any persistent state. All that state is typically in a database. And the web server is talking to that database via SQL, right? So this is your classic kind of three-tier web application design. And so what we want to do in this work is to, in addition to this setup, we want to associate a little policy with the database that describes who gets to see what, who gets to update what, and so on. And then we are going to sort of make sure, using a method called information flow control that I will explain in this talk, that policy is maintained throughout the web application, throughout the database and the web server, and that all the clients, so we do not check the clients. The clients are just, they're completely untrusted JavaScript code. But we're going to make sure that all the data that a client can access is as mandated by the policy. Okay? So good. Let me give you the sort of high-level structure of the talk. It's going to go like this. Hopefully I've motivated why you want to secure web applications. Next, I'm going to give you a kind of demonstration of how does it, like, what do you do? If you are a Storm user, programmer, whatever, how does one go about securing applications with Storm? After that, I will give you the kind of the technical part. How does Storm really work? What's going on under the covers? Okay, I'll try to explain that not too briefly, but somewhat briefly. And then finally, I'll tell you some things we did in order to determine if Storm is actually useful. Can you really build web apps with Storm, or is it just a kind of vaporware, as they like to say? Okay, so let me pause and say, by the way, I switched off my video just so that I can look at my screen. I have only so much real estate, but if people have questions, please just jump in on the audio, and I'm happy to stop anytime. And I prefer it if you just did that, right? So just jump in and ask me whatever. Okay, so things are unclear. Okay, so let's look at a quick demonstration of how does it work? How does Storm work? Or what do these web apps even look like? Okay, so imagine we're making a kind of a toy web app, right? And in this web app, it's a kind of wish list, if you wish. So where I guess Christmas is coming up. So imagine you have a kind of wish list. So you have users, and each user has a list of things that they might want. They might want to get, if you wish. And maybe some of those wishes. So for example, here's a user, that's me, and then maybe I want the Godzilla movie, and I want. Yes, sorry. No question. I might want to learn how to program. And so I have a bunch of these wishes and their associated descriptions and prices. And maybe some of these wishes are marked private because for whatever reason, I don't want everybody to know that this is something that, I'm interested in. Okay. So now imagine I have a policy that says that only the owner of a wish, so that is to say Ranjit, me, can access a wish that was marked private. Okay, so all the other wishes are not marked private, they're public or whatever, so anyone can see those. But the ones that are marked private should only be accessible to me. So here's how one goes about sort of, here's a kind of web app 101 type of, explanation. So in this web application, what you would typically do is you would describe what your database schema looks like. This is a kind of a standard thing. You have these kind of schema libraries and, pretty much all languages. We're using one for Haskell. And in this schema, I would say, okay, there's a table called users, and each row of the user has a name, the user's name and the user's email, right? And then there's a separate table called wish, and the wishes comprise the owner, who is the person who owns that wish. Let's just say a title, some description of that particular wish, if it was the Godzilla movie or the karaoke machine or whatever. And a level, and this level is going to be the security level, right? And so we'll just say it's a string. We'll just use public or private to denote whether or not they're supposed to be private or not, okay? So here's my policy. Remember, my policy was only the owner should be allowed to view a particular item if it's marked private. So this policy now is, I'm giving it a name because I'll use this policy in a couple of places. I'll say only public, policy only public is defined as, the policy is going to be a function, a predicate, if you wish, over a wish, right? An individual wish item and a particular viewer. So it's a Boolean predicate that says, given a wish and a viewer, is this viewer allowed to access this particular wish? Okay. And what we're going to say is that, well, a viewer can view this wish if the wish.level, so the level field of the wish, is marked public, or the owner of this wish, so wish.owner, is equal to viewer. Okay, so this is essentially saying, in precise terms, what we meant by only the viewer should be able to view private things. So either the wish is marked public or only the viewer can view it. Now what I'm going to do is I'm going to attach this policy, and literally I'm showing you the concrete syntax, right? You write this policy and then you attach that policy to that field, to the title field, and you say, okay, this field should only be viewable to those users who are either the owner or if the string is, if this level of this particular wish was marked public. Okay. So now let's look at that was the policy specification. Now let's look at the actual web server, the application's implementation. Okay, so imagine the way these web servers work typically is you have essentially what are called routes.
Ranjit,
so when yes.
So the policy will be attached to the record itself, right? Or any field of the record?
It can be attached to individual fields. So you can have different policies that are attached to different fields of the record. But so in this particular case, it is only attached to the, this only pub is only attached to the title field. If you like, you can attach it to other fields also. But in this specific example, I'm only attaching it to the title field.
Okay, but the policy can refer to other fields. Okay.
Policy can refer to other fields. That's absolutely right. The policy can refer to all the other fields, but as far as enforcement is concerned, we are going to attach it just to the title field, right? And it's actually important for it to be able, I mean, both the questions you asked are actually related. So for example, if you think about this, the level field, everybody can view. And it is important for everybody to be able to view the level field, because otherwise, how will I know if the thing is public or private? In the actual code, I'm going to determine if a thing is public or private. And I want random people to be able to see, hey, is this field public or private? You see, because otherwise.
So you want a level field, right, for everyone? No, I have a question there, right? So I have a question. So suppose there is a restrictive policy on one of the fields, like title.
Mm-hmm. Correct.
And you want to also put a policy on the entire wish record.
Mm-hmm. Mm-hmm.
Do you have some kind of ordering on that the policy governing the entire thing should not be, whatever, it should be at least as strong as this or whatever?
Correct.
You have some kind of constraint like that?
Correct. Yes, so that works out, Sanjeeva, just kind of, you get this kind of lattice on the policies directly from a
you do have a lattice. So you do come down to Denning kind of lattices?
It is, but it's not an explicit lattice in the sense that we absolutely have a lattice, but that lattice is kind of implicit in the implication order of these predicates.
Yeah, so you have some kind of some logical ordering and so on, right?
Correct.
Great.
Yep.
So I have a question. I mean, if I attach only pub to level, then that would be a type error, or I mean, I don't know. Like
it would not be a type error. You could attach it. Oh, sorry. At this level, sorry, level is a kind of overloaded word. In the screen we're looking at, you can attach things wherever you like. It's when in the code you try to access the level, you will get the you'll get a type error, because it'll say, hey, you have this policy only pub, but that says only the you can only view this field if you were the owner or whatnot, but you are not the owner and you are viewing this field. So let's just this particular, that's a great question. So let's come back to it after I show you an example of what the type checker does.
Okay,
that's okay.
Sure.
So Ranjit, I have a question. So
Yes.
Can we compose the policies, or can we attach multiple policies to the same field?
Yes, you can. So since the policies are just predicates, you can just conjoin them. You can literally just write, you have policy P1, P2, P3, and you can say policy P5 is P1 and P2 and P3 and P4. You see what I'm saying? And then that's.
Yeah, I guess that comes back to my question, because you've basically got some kind of implicational logic out there.
Correct.
I want to get a little ahead. Maybe I'm getting a little ahead. Is there some sort of dependent typing that you're planning to do in this?
Oh, yes. It's all dependent. Everything here is dependent typing. Because,
okay, great.
I mean, as you can see, the policies depend on the values in the database. Right. Just looking here, right? Because level is a value and
Sure. So, I mean, so this is grounded there.
Absolutely.
Okay, great.
Okay, very good. So let's look at this. So I think this is where to perhaps this will sort of get towards Saurav's question, which is what would have happened if you attach the policy on that on the level field. So here we just have the policy on the title field, but let's look at this snippet of code. And as I was saying, what typically happens is when you go to your client, you're running the application, you hit some URL, right? You enter some command, whatever, you do some interaction. This interaction fires a AJAX, whatever you want to call it, an HTTP request. And this HTTP request sort of hits the server, and the server then sort of looks at the payload in your request and issues some database queries to figure out, how to construct a response, and then a response, and then sends that back to you again via HTTP, right? So here's a very small kind of a toy illustration of that particular cycle. So this is a particular what is called a controller in web app speak that responds to a query for showing the wishes of a particular UID, let's call it user, denoted by UID, right? So let's see what this controller might do. The controller would first construct a database query. So the database query says it constructs a predicate. So think of this as literally the query object, if you wish. The query says owner must equals UID. And then it executes this query using a select operator, right? This is like the SQL select, if you wish. I'm sort of reusing that name. And so what this is going to do is it's going to run the database query, this particular query, to find all the wish rows whose owner was UID. Okay, that's what this select does. And then in the next line, what we're going to do is we're going to think of this project as kind of just pulling out the title field of all of those wishes. So wishes was an entire collection of wish objects. And what I'm saying is, hey, take that and essentially run a map function, if you wish, for those who are familiar with functional programming, to pull out the title field of all the wishes, to get all the titles, and then finally respond to the user with some, JSON object or what have you, with all these titles, right? With all these descriptions. So imagine that we had written a piece of code like this. Now what would happen is Storm would essentially yell at you and say, sorry, you can't do that. That respond titles violates your policy because these particular wishes are all owned by UID, right? They belong to UID, but the person that I'm responding to may not be UID, right? So these titles, because of the policy associated with title, are only viewable by UID unless the wishes were marked public. And so since I'm sending the response back to some session user who may not be UID, this is a kind of violation of the security policy. And Sanjeeva, we'll go back and tie this back into the lattice view, in a little bit. I just want to give a high level demo right now, right? And so the way you would fix this is basically to say something like, no, you can't give all of UID's wishes to this random viewer. What we want to do is to restrict the set of wishes that we send back only to those wishes that are explicitly marked public. Okay, so if the session user is not UID, then we want to restrict the wishes to those that are marked public. So here's a snippet of code that does that. Let's look at it. It's there's a little bit of work here. So same thing, show wishes. Now what I do is I get the session user. I have some API call that says, hey, who's the session user? And now I have, this is just a C style if then else, if you wish. If the viewer is equal to user ID, so if the current viewer is in fact the same person that we're trying to get the wishes of, then this query fragment is true. There's no extra constraint. So here what I'm doing is I'm generating an extra constraint. This query has this extra conjunct subquery, if you wish, that checks if the level is public when the user is not the owner, okay, when the viewer is not the owner. So what does this query look like? Well, it's true in the case where the viewer and the UID are the same. But in the case where the viewer is not equal to UID, I put in this query fragment, level is equal to public. So it's literally that sort of query snippet. And now, so I'm essentially dynamically generating this SQL query, if you wish, depending on the value of UID and the session user. And I'm going to again run select blah. And this time, the type checker is going to say, okay, in that case, this is all good. Okay, this actually conforms to your policy. Okay, so let's look at a slightly more involved example, because there in the previous example, the policy is just referred to data within the same row of the database, right? Oh, you can look at the title if the public field was marked public, right? Sorry, the level field was marked public. Let's look at a slightly more involved example, where now this user Ranjit Jhala has also acquired a bunch of friends or followers. Okay, so all these little characters off on the right are my friends. And somehow I want to weaken my policy a bit to say that the private things should be visible to my followers. Sorry, is there a question?
Yeah, there's a question. Just 1 minute. Can you go to the previous slide?
Of course, yes.
So it looks like you're applying your selection, your query on the whole record itself, right? Because you're only later projecting. So is it possible?
Correct. Absolutely right. Absolutely right. So the select returns the whole record, everything. And so at this point, the user has not actually seen anything. It's still kind of a box. I mean, it's an opaque object. It's only at this point that the actual access happens. That's a very good observation. Yes.
So it is okay. So in some sense, yeah. So in some sense, it's not modular in the sense that you have to know which things you are projecting to before you apply this query. Because if you were just revealing the levels, let us say, then you wouldn't need this.
Well, you in fact see it's completely modular. So what's going to happen is, think of it. I mean, I don't want to get ahead of the game, but what's happening is over time, by time, I mean, if as these statements kind of progress, we are narrowing the set of users who have access to the data that computation depended on. So at this point, all the data that we touched is not really sensitive. At this point, it's still not sensitive. Even after you execute this select, the data that we touch is not sensitive because you haven't actually looked at anything sensitive. But when you do the project, at that point, you are going to say, oh, you're looking at the title, and now only these people are allowed to look at the title. And so essentially what's happening is, as we sort of progress across time, you keep conjoining, or in Sanjeeva's terms, you keep going down the lattice of who is allowed to have access to those results. And this is kind of done in a compositional fashion. As I'll get to it in a bit, hopefully.
Yeah, thanks.
Okay.
Okay,
good. Sorry, is that a question?
Yeah, I'm so sorry. I had a quick question though. Doesn't this actually correlate to role-based access controls that are existing in the database? Because I'm asking to understand if viewer is an object or is it a field of the database?
Viewer is just a database value in this case. Okay. In this particular case, viewer is just a database, and this very much has sort of connections to the kinds of constraint checking and whatnot that one does in a database, except that we want to kind of make all our guarantees at compile time. So I don't want to do any kind of runtime checking. So everything I'm describing, so when I say this safe, unsafe, all of this happens at compile time. You write the policy, you write the code before a single instruction is ever run. Or even before the database is created, really, all of this type checking is going to tell you if your code conforms to the policy. So that's the main kind of extra bit that's happening here.
Okay, thanks.
But you're right. Access control is a kind of very, very special case of the kind of thing we're talking about.
Ranjit, can I ask a question?
Yeah.
This language that you're showing, is it some new language you're proposing, or is it like a standard language?
This is Haskell.
The language that you're showing in the current.
This language is Haskell. It's an existing language, and everything I'm describing to you exists. It's the tool that I'm describing is a kind of compiler plugin. So,
okay.
And it's kind of important that it be. I mean, it was an important design decision, partly because I'm sort of this. We'll talk about at the end of it. We built a couple of web applications, and what surprised me when I built these is, we only wrote our web server was like, I don't know, 2,000 odd. There's a table. We'll see what the exact number is. Around say 1,500, 2,000 lines of code like this. But in order to actually get a real web server running, when we sort of hit make, and they were downloaded, I kid you not, 150 different packages. And all of these packages were doing things that were important. One is like talking to the database, JSON serialization, crypto for HTTP, blah, blah, blah. So anyway, all of this is a real language. And I'm just, this is just Haskell syntax. What is less known about Haskell perhaps is you can have little semicolons and curly braces if you like. So I've just put this in to make it look a little more familiar. But yeah,
Ranjit, so is this a GHC plugin?
It's a GHC plugin, yeah.
Okay, cool.
Yep. Okay, great. So where was I? Yes, my wish list with friends. So same wish list. Remember now, some wishes are private, but now I have these extra followers or friends. And now I want to tweak my policy so that it looks like this. Okay, only followers. Maybe I should skip this part in the interest of time. Hang on, let me just see what the time is. Oh gosh, we've blown through half an hour. Maybe I'll skip this bit just to get to some of the technical parts. Long story short, suppose you want a policy where only followers can access the, this should be, can even access the public wishes. Now, I don't even want to allow the public to see the public wishes. Private wishes belong to me. Followers can access the public wishes. I might add a separate followers table that says, I am the user, this other person is my follower, right? And there's some status which says, was it accepted? Because anybody can request to follow me, but then I must also accept in order for them to really be my follower, right? So anyway, long story short, you can essentially have a notion of an accepted follower that says F is an accepted follower if F.status is accepted and this Boolean condition holds between the follower and the user, between the user and the follower fields. And now you can sort of boost your policy a little bit for the title that says either you are the owner or the wishes level is public and the particular viewer is one of your followers. So essentially you can now you can also write policies that span across the database, across other tables. In this particular case, you are allowed to view this only followers depending upon the value of some other field in another table entirely, right? And the same kind of thing happens. If you have a piece of application code like this, now imagine I want to tell all my followers my birthday is coming up and I want to send them, I want the email to go out saying Ranjit wishes the following 10 things we bought to him. What a terrible app. Anyway, you might write a query that looks like this. Wishes is, this is the owner, owner is UID and level is public. So you pull out all the wishes. Then you get a list of all the followers. So you get all the, essentially I take, find the list of all the user IDs. The table, I find the user follower pairs and I project out the follower field and I select the case where this particular user is in one of the follower IDs, right, that I previously computed. And I send an email out, right, to all the followers with the titles. And again, the type checker will complain and it'll say, no, 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 this is not correct. Because remember the policy mentioned that the status must also be accepted. Okay, it's not enough for just that pair to be in the followers table. The status must also be marked accepted. And so now you have to strengthen that query with, oh, correct. It's not just that the user was, the source user was UID. It was also that the status was accepted. And once you do that, then the type checker will be happy with it. Okay.
I have a question. Can I ask you?
Yes, absolutely. This is a great time to ask questions. Yeah.
I wanted to see, because the level and many names or fields are available to the public, can't one do some information disclosure attacks so that one can try to find like many of the Boolean operations and to say that if I'm going to get his GPA, if I know all the other person GPA -1, can't I do that? Because if many fields are known, I would be able to do that.
Yes. So the kinds of guarantees that we would give you, that we can give you, are, what are called the classic non-interference style guarantees. But which is to say that, if you are a user and we literally erase. So again, to go back to what Sanjeeva said earlier with this lattice, right? If you erase all the data above a certain lattice level, which this user is not supposed to have access to, and you replace it with some other data, then you execute the code and you run 2 executions of the system. To this user, the executions are indistinguishable, right? So this is the kind of guarantee that we give you. But it's entirely possible that you can make some statistical correlations of the kind that you are describing, and that is outside the scope of this particular work.
But your web application allows the database to be changed, right? Can be written, read, and all that things, and also delete, and also delete. That would also allow for some leaks, right?
Yes. So again, you have to. In all these situations, all we're really doing is we're letting you centralize the policies for how you read, update, and delete, right? All of those are guided. I just showed you reads over here, but the same thing you can do for delete and update. The same kinds of policies can be applied to those, right?
But in what way it would be different? Like in language security, if you attach the labels to the various fields or the other, to say that who are the readers, who are the writers, etc., kind of a thing or the other, I can have different sectors, right?
So the main difference with classic sort of label-based, language-based security, so I imagine the kind of thing you're referring to is, say, things like, I think it's called SE links is one example that comes to mind. Is that you don't have this pesky business of labels. So there's, actually there's another, we'll look at LIO, label.io, that's another system we compare against, is you don't have this, I'm just going to say it, it's slightly pejorative. It's very pejorative. We don't have this nonsense of having to manipulate labels, which is this kind of extra notion that doesn't really exist for the app itself. Here you just have the app. And in a sense, what we are giving you is, you can think of these little logical predicates as labels, but they are implicit labels. It's not something you have to worry about yourself as a programmer, which is something you need to deal with in the label-based world, right? And
but that also would place a restriction to say that all computations can be done, those that do not require label changes, dynamic label changes. Like LIO has some label changes that happen kind of a thing or the other, right?
Right, and you don't have to fiddle around with all of that, right? So in LIO, the programmer has to be very careful in kind of manipulating labels carefully, and there's none of that over here, right? Okay, so
Ranjit,
let's see. Yes.
So just to check my understanding about something that Professor Shamsundar raised. So, so it wouldn't be a problem in your app if you did a sum function, let us say, because you don't need to check at the level of the sum, but when you do a select, it will already catch it, right? Because you would have read a GPA field of some record which was private or something.
Correct. Absolutely right. That's absolutely correct. Yeah. In fact, I don't have time for it in the talk, but there's a paper that describes this work, and there's an example that's like that, where you do some sort of implicit comparison, and Okay. So how does this work? How exactly does Storm, like what is happening? Okay, so let's go back to this particular picture. Remember, there's this 3-tiered application, and what we're going to do is essentially the way this. What I like about this tool is that it's not really a tool. It's in fact a type checker, and the type checker is a very general tool. All of the stuff that I described to you happens by figuring out appropriate types for different layers of this ORM. Okay, that's hence the name Storm. Okay. So in order to explain that, let me just go back to this very simple example we had, and I'll try to explain what I mean by we're just refining the layers of the ORM. So remember, there was this show wishes controller that I showed you right up at the beginning, right? Where you UID and so on, right? I check who is the user and I will check if the level is public, etc. So now think of this entire snippet as the server code. Okay, sorry, this went too far. That entire orange box is the server. Okay. This entire orange box is made up internally of a sequence of sub-expressions, sub-computations, if you wish. I'm going to call those computations actions. So I'm sequencing all of these yellow actions. Okay. All of those are, let's call them actions. So I'm at the bottom over here, I'm telling you what these different entities are. So the top level thing is the server that runs. The server is made up of these yellow actions. Let's zoom in on one of the actions. This action itself is this, in this particular case, is a database query, right? It's a select function. But this select function itself takes as input a database query. So you could have select, you could have this project. Both of these are different database operators. There's various others, join, etc., right? So each action is made up of a query using the select and project API. And finally, if I zoom in on the queries themselves, the queries are themselves made up of subqueries which contain fields like owner or level and program values like UID and what have you, right? And of course, subqueries themselves like query, okay? So in a sense, my entire web application has these 4 different entities. There are fields. I combine fields using operators like equals, and or not, whatever, to build up queries. I take these queries and I execute them using select and project to get actions. And then I take these actions and I compose them sequentially. That's what this semicolon is doing. I chain a bunch of actions and that gives me my server, okay? For those familiar with Haskell, the way the sequencing happens is with this bind operator, the sequence operator, which I'll describe in a little bit. And so now the way that Storm works is essentially, we're going to associate types. We're going to start with your policy, the thing that you wrote, with the orange at only pub and all that kind of thing. We're going to start with those policies, and then we're going to associate types with each of these operators, equals, and, select, project, etc., such that the end-to-end type checking guarantees that your code satisfies the policy. Okay, that's really what's going to happen. So I'm just going to now show you essentially each slice of this, of this API. If you think of this as an API, I'm going to show you what the types look like and how they need to be in order for you to get this end-to-end guarantee by type checking. Okay, so I'm going to break it up into, I'm going to sort of break up this technical part into 3 portions. First, I'm going to give you a very whirlwind overview of refinement typing. What does that even mean? Okay, and for those who are familiar with Floyd-Hoare logic, it shouldn't be, it's very much like Floyd-Hoare logic for our parts. And I'll tell you the bits that are different. Next, I'll explain this bit about what are these actions and how is it that we compose the actions together to build up a whole server, and how exactly does information flow tracking happen there. And finally, in the third part, I'll explain how these actions get connected to the queries, the underlying database queries, and how those are connected with the policies. Okay, so let's just sort of keep this roadmap in our head, and let's start first by looking at what is refinement typing. Okay, so here is, I mean, for those of you who know this, I apologize, but just, to make this talk self-contained, I had to put some of this in. A refinement type is basically, think of it as like a plain type, like int or bool or string, but together with a logical constraint of this form, like x greater than 0. And typically, I'm going to rig it so that these constraints are all going to be from a decidable logic. Okay, so here it's the logic of linear arithmetic, and we can have uninterpreted functions. Okay, so this is a refinement type that essentially describes integer values that are non-negative. So int, x is an int such that x is greater than 0. Okay, this is a sort of absolutely straightforward refinement type. Now, this is an example of once you have refinement types as inside functions, you start getting contracts like pre and post conditions. So this is a function type as denoted by this arrow. And the left-hand side of the function tells me the input type, which you can think of as a precondition. And the output type is, well, the output, which you can think of as the post condition. So this essentially describes a function that expects as input integers that are non-negative and returns as output integers v that are greater than the x. So for those familiar with the notion of dependent typing, this is a kind of dependent type because the output can refer to the input. Okay, that's a precondition, that's a post condition. I thought there was a question somewhere. No? Okay, very good. Now, the way refinement type checking works is, I mean, it's very closely related to how Floyd-Hoare logic works. So imagine I had a piece of code that looks like this. I have a function called double, which takes as input x and it returns 2 times x. It's not a very exciting function. And what I want to prove to you is that this function satisfies the following contract that says if you call it with inputs that are non-negative, then you will get back as a result values that are greater than x. Okay, so how does the type checker verify this? What it does is it builds a verification condition. So essentially it takes the snippet of code and it takes the type specifications and it crunches into a logical formula that looks something like this. The formula says if x is greater than 0, which you get from the precondition, then the value that is equal to 2 times x, right, the body of the function, if the value is equal to 2 times x, that implies that the value must be greater than x. Okay, so I don't want to get into the algorithms of this. That's somewhat outside the scope of this talk, but hopefully you can buy it when I say that you can take a piece of code that looks like this and crunch it into a logical formula that looks like that. And then you take this formula and you ask an SMT solver, for all x and v, is this statement true? And the SMT solver will say, yes, why it is true. Now, at this point, it is common to ask me about integer overflows. For the purpose of this talk, we're skipping integer overflows. You can model that as well, right? Let's just pretend these are like God's integers and they go off till infinity. Okay. So now, the first sort of extra magic sauce that we have to use in this particular talk, and I will describe this very briefly because this is also described in a line of papers that I don't want to get into the details of. Imagine I write a function called quad, which uses the composition operator. So this dot is the function composition operator. And the function composition operator looks something like this, right? F.g. I'm using infix notation. I apologize for folks who might find this difficult. Read this dot as just compose. Okay, so compose fg is equal to a lambda term that takes as input some x, and then it runs g on x, and then it runs f of g of x. Okay. Now the question that I have is what is a type that I can assign to the compose operator, this dot, such that I can prove that quad also has the same behavior, that it takes as input, if you give it a non-negative, you get back a value that's greater than x. What is the suitable type for compose? So it turns out this is tricky because I want to give compose a type that has nothing to do with double. It has to be generic over the specifics of integers and multiplication over here. Okay. And so we came up with this trick of what is called an abstract refinement. So think of it and make an analogy for those of you who are familiar with functional programming. Just like you have types, you can write your function takes an integer and returns an integer, or you can have polymorphic types where you say for all alpha, a function takes output an alpha and returns as output an alpha, right? In the same way, you can essentially do the same thing with refinements, where what you can say is, this function takes as input an integer such that some p is true. I don't know what the invariant p is. There's some invariant for any invariant p. If you give me an integer satisfying p, then I will return to you an integer satisfying p. Okay. And you can take this particular idea and you can sort of really, put it on steroids in the following fashion. I can give compose the following type, and I'm going to try and explain this to you very slowly. So what I'm going to say is that imagine there are 3 relations, 3 invariants, p, q, and r, such that the compose function, remember, takes as input f and g. And the first function f should map values of type b to c. The second function should map values of type a to b. And so the composed function takes you from a to c, right? If you just look at the green bits, it just takes you from a to c. Now, additionally, what I'm going to say is that the first function produces some postcondition q that relates the output value v with its input y. I don't know what q is for all q. Okay, q is something that is to be determined at the call site. There is some relation q that holds between the output of f and the input of f. Similarly, there's some relation p that holds between the output of g and the input of g. Okay, and if you give me f and g that have this behavior, then I will give you some value c that is related to the input x by this relation r. If, and now this is the magic bit, the following horn constraint holds between p, q, and r. So this thing down here, I'm calling it the compose horn constraint. What it says is the relations p, q, and r are such that for all x, y, and z, if p, x, y is true and q, y, z is true, then r of x, z is true. Okay, so I hope people are familiar with a horn constraint. If not, it's a logical implication that looks like this. Okay. So essentially what we can do is we can give compose this very fancy looking type signature. Okay. where P, Q, and R, for those who are familiar with the SMT literature, these are just uninterpreted functions. So it turns out that all the checking remains decidable because P, Q, and R are just uninterpreted functions, and you can make all of this work out quite nicely. And furthermore, what's going to happen is that we can automatically synthesize at the particular call site. If I have this particular, P, Q, and R, these horn constraints, we can sort of automatically instantiate them at any call site, and that will allow me to prove that quad has the type, takes a non-negative and produces a value greater than X. Okay, so there's one thing to take away from this slide. What we're doing is we're writing function signatures, but we're going to allow you to quantify these function signatures over these relations like P, Q, and R, and you can now relate these relations using horn constraints. That's the high level bit. Okay, we're going to use this in order to build up our API. Okay, good. So that's refinement typing 101. Let's take a what? I have 10 minutes left. Good God. Okay, let's see if I can get to.
We started a bit late, so you can take a few.
Maybe I can take maybe a few more minutes. Okay,
maybe you can just say number 2 is monadic.
Can I say that? I don't know. There's a little bit more than that going on, but anyway, let's see what's happening. Okay, so how is this action in the server, right? So as Sanjeeva said, the 2 is monadic. So if you look at this controller, so this is a very nice idea that my colleague Nadia Polikarpova had, where they observed that, okay, if you look at this controller, it's a sequence of these computations, right? So remember, we're trying to figure out this server. And we're trying to do information flow control, right? So the key idea is the following. For each of these sub-computations, so you can think of the entire show wishes as an entire computation, and you can think of each line or each statement here as a single computation, a sub-computation. We are going to track 2 sets of users, okay? The first set of users is the set of authorizees, which I think of as the set of users allowed by the policy who are authorized to access that particular data. Okay, so for example, if I look at that if I look at that computation where I do these 2 things, the authorizees are going to be the set of users that is exactly equal to UID. Remember, because the policy said we're looking at the title, and the only person who's allowed to look at the title is the user of that particular wish. Okay, so the authorizees for this computation are, I'm writing it as a predicate, lambda u, where u equals UID. Okay, it's a set of users. This is denoting a set of users that is the singleton set equal to UID. Okay, now if you look at the next bit of the computation, we're also going to track the observers, which is a set of users who are provided access to the data. Okay, so in this particular case, this respond action, if you wish, the respond computation sends the response out to the session viewer, right, whoever's logged in this session. And so the observers are lambda u equals session user. Okay, now the crux of information flow enforcement is like this. Whenever I compose 2 computations, okay, if I have one computation who has some authorizees auth, and I sequence it with another computation who sends information out to some set of observers, then the set of observers must be contained, of the second computation must be contained in the set of users allowed access by the first computation. This is the crux of the policy enforcement. Again, this is, by the way, this is the whole lattice thing that Sanjeev was referring to. You can sort of turn the subset into like a lattice square subset and so on. Okay, because if you send the data out to more observers, then essentially you are sending you're sending data from here, you're making it available to someone outside the set that was authorized. Okay, so now in this particular case, we got a type error because we do the same kind of check, and this set inclusion becomes a logical implication, just like the VC that I showed you. It in fact becomes a VC check because of how we set up the API, but I'll get to that in a bit. U equals session user, does it imply U equals UID? Absolutely not. And so the type checker rejects the code. If instead, if I change my code so that I add this extra conjunct, level equals public when viewer is not equal to UID. Now, if you sort of crunch the numbers, or if you crunch the logical symbols, if you wish, the set of authorizees for this particular subcomputation is in fact the set of all users. And the set of observers now is still the session ID. And so your policy enforcement check becomes something like this. U equals session user, is that contained inside true? And of course, everything implies true, as I learned from Sanjeeva many, many years ago. And so this check passes. Okay.
Ranjit, one question.
So now, yes.
So because of this, observers is a subset of authorizees condition. Even if you don't do the project and the select in the same snippet of code, but you have them as two different, let's say, actions, and then you compose them, it will still check correctly.
Absolutely. That's absolutely right. You can have them scattered all over. The moment you glue the actions together, you'll say, oh, now we're going to conjoin the observers and authorizees, as we'll see in a second. And at the point where you do the sending out, that's where it's going to check, okay, what did you when you compose that with the rest of the data access is when the check happens.
Okay, so this was what I had a doubt earlier when I thought it was not compositional, because you had to put all the queries at the point where you do the project, but you don't need to.
Right. Okay. No, they can be scattered all over, right?
Okay, thanks.
Okay. So now the way all of this works is, so that was the high level bit, right? We're going to track these observers and authorizees. The way we track them is as the functional programming way of saying it is as effects in the action monad. And if you are just a more classic sort of program verification person, you would say we track them as ghost assertions for each statement. And we sort of have contracts for the sequential composition that essentially lets us compose these ghost assertions to track this authorizees observers for entire computation. So let me show you how that happens. Okay. So think of each of these yellow snippets as a monadic computation yielding a T value. So it's an action T. Think of it, if you prefer, you can think of it just as a statement. Okay. Each of these yellow things is a statement. Now what we're going to do is we are going to refine the types of these actions to kind of refine them with this. It's going to be a set, but for us, sets are just logical predicates, okay? And one predicate describing the authorizees and another describing the observers, okay? Now let me show you, okay, how do we track these sets? So when you have a return function, this is in the monadic return, basically says that it's a pure action. So it doesn't touch any sensitive data, okay? Return just takes the value A and returns a computation, an action that produces an A. It doesn't touch any sensitive data. And so the authorizees are all users, so lambda u arrow true. And the observers are no users, so lambda u arrow false. Okay. The more interesting operator is, well, let's look at the respond operator. Okay. So what we say in the respond operator, you get some text that is sent back as the message, right? But the action has the type. It does not access any sensitive data. And so the authorizees, all users are authorized, right? But the observers are just the session user. Okay, so each of these sort of primitive APIs things, we give a thing like that. The really interesting one is the sequencing operator or the bind operator, which looks like that, which folks who are familiar with Haskell can sort of follow the nitty-gritty. For the rest of you, just think of it as it takes one action A and another action B, and it sequentially composes them to give you an action B. I'm lying over here a little bit. And here's what the type looks like. Okay, so if the first action has observers A1 and authorizees A1 and observer O1. The second action has A2 and O2. The resulting action has authorizees A and observers O, where, and this is this composition, right? The following constraints hold between O2, A1, A1, A2, and so on and so forth. Let's look at it, right? The first bound says that O2 must be a subset of A1. It's exactly that thing I showed you earlier. The observers of the second action must be contained inside the authorizees of the first. So you can write this as a horn clause. Basically, it says O2 implies A1. Second, we want that the action, the authorizees of the composed action are the intersection of the authorizees of the first two actions. So if you take the authorizees of A1 and the authorizees of A2, only then can you be authorized to see the results of the entire computation, okay? The observers, on the other hand, are the union of the observers of this one and this one, okay? And so you can write a little horn clause that lets you say that. And so all we have to do is just say, okay, this is the type of the sequencing operator, and that's basically it. Okay, that's how we encode the information flow. The last bit is, okay, that's great. How do we actually figure out who the authorizees are? Where do we get the how do you connect the security policy with the primitive, the database access, the select project, and so on and so forth? Oh gosh. Okay, I can take 5 more minutes, right, Deepak?
Yeah, Ranjit, sure.
Okay, very good. So let's look at, this is the kind of the crux of the matter, right? So this is part 3, if you wish. How are we going to track the authorizees from the policy? So here's the plan. What we're going to do is, we're going to remember how we associated those orange snippets with the database fields, right? So think of it as we're going to inject the policy. Yes. Yes. Yeah.
Sorry, I maybe missed a part of this. What does authorizee mean? I understood observer, but I did not understand authorizee.
It's very tricky. The authorizees are the people, are the set of users who are allowed to view that data who are allowed to view the data underlying that computation, used by that computation according to the policy. So let me rewind a second. Okay.
So if it's a single action, if it's a single action without a composition, the authorizee should be a subset of the observers, is it?
If it's a single action, if it's a single action, it doesn't matter typically because the actions, any one action either has an authorizee or an observer. Either it talks to the database or it's sending messages out. You see what I'm saying? But you're right. For a single action, we're just assuming that each of your primitives are not leaking. I don't magically project and send everything out, right?
Okay.
So primitive, yeah. So does that make sense? So the authorizees here are who is allowed access to the data that this computation depends on, basically, according to the security policy.
So isn't it that the observers in the second statement should be contained in the authorizees in the first, right? That's what you.
Correct. That's exactly so. Where did I? Here we go. The observers in the second statement must be contained in the authorizees of the first.
Yeah. So right? I think Raghavan said it the other way around. So I don't know.
It's quite easy to get the implications wrong.
No, Deepak, I said the right thing, but I was talking about just one action, assuming that the controller has only one action. I said the observers have to be a subset of the authorizees.
Okay.
Yeah. Okay. So tick, give me a moment. We'll come back, blah, 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 action monad, etc., etc. Okay, great. Okay, good. Now how to connect to the wretched database? Let's see. Blah, 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 blah. Oh, seriously. Okay, here we go. So here's what we're going to do. Remember, the first step, we have these little policy predicates that are associated with the database field, right? So we can conceptually think of it as we're going to inject the policies in the database field. Then as we build up the database queries, with the equals and the and all those little query combinators, we are going to sort of associate, we saw these are the people allowed to see the field, and now I'm combining two fields in a query, and I'm combining subqueries. I will sort of, with each query, I'm going to make up types for equals, and, or, and whatnot, so that I can precisely track who is allowed to view the results of that particular query. And then finally, when I do an actual select or a project, I will be able to extract the set of authorizees at the point where we do the query execution, okay, via select and project. So let's see how you inject the policies in the database field. So remember, this was our database schema, user and wish. And so the standard thing, this is what a standard ORM does. This is the Haskell version, but the Java version does the same thing, and the Rust version does the same thing. If you have a user table, it'll create some representation of a field called name and a field called email and a field called owner, title, and so on, where it'll say, okay, name is a field of the user table and the field has type string. Owner is a field of the wish table and its type is user ID, right? So different ORMs have different ways of doing this. What we are going to do is we are going to take this plain sort of programming language type, which says that I'm a field of so-and-so table named row and I have the type val, and I'm going to decorate it with two logical predicates. First is, of course, going to be the authorizees. According to the policy, who is allowed to read those fields even, right? But the second is equally important. It is going to be a representation of what that field's semantics are. So it's these are both going to be so they're going to be predicate take the row, and in one case row and the user and return true and false. The other is going to be a predicate that defines what value is even held in that particular field. This is easiest to just see by an example. Okay, we're going to represent we're going to have to represent the SQL query semantics at the type level, and that's what this rep does. So here are some examples. Let's just look at the owner field. The owner field, remember, anyone is allowed to view it, and so the predicate is just all, which I'm just writing as a as lambda u arrow true if you wish. And the semantics is that given a row and a value, this value is equal to the owner of this particular row. So think of this as a logical representation of what's inside that row R. Okay, so again, an uninterpreted function. This, in the case of title, in this case, the policy is not all, because in fact, it can only be viewed by the owner unless it's marked public. So it's its own predicate, where the own predicate is either u is equal to owner or the level is equal to public. But now the semantics field, if you wish, this representation field says that the value is equal to title and so on. Okay. So that's how I inject the policies inside the database field. Next, I'm going to make up types for the equals and this and other combinators to give me a type for the whole query. Okay, so remember, here's my query. Suppose I had a query like this, right? To find the public wishes of UID, I said owner equals UID and level equals public. And so what I need to do is I'm going to take this query object and I'm going to again refine it with two things. First is who is allowed access. And the second is what exactly is in that? What is that? What do rows in this query look like? And this is going to be very important, as we'll see in a second. Okay. So for example, if I have a query of this type, query where the authorizees are own and the level is equal to public. So set of authorizees is the owner of the record unless the level is public. And the invariant says that every result in this returned by this executing this query has a level that's public. Okay, so for example, that's what this particular query says, that when you run this query, every row that you get back is going to be marked public. Okay. Now, the query builder API, the equals, less than, and, or sort of maintain this invariant. I wonder if I have, okay, let's look at the type for the equality operator. It looks something like
Ranjit,
this, right?
I got a little confused about that previous slide.
Yeah.
It said that every row that is returned, it's guaranteeing that the level is public, even if the query is by the owner?
Even if yes. So I'm just
okay, because it implies public. It's higher in the lattice than public.
Exactly.
Okay,
So
great.
exactly. So it's higher in the lattice. Exactly. There's an abstraction, right? Okay. So hence the word invariant, right? Okay. So that's an excellent point. You can kind of weaken if you wish. Okay. Equals. Okay. So this is the type of the equals operator. So the equals operator takes a field and it takes a dynamic value, right? Some value at runtime, user ID or public or whatnot. And it returns as output a query. And the important thing is, what is the policy on this query? So who is allowed to view the results of the query? The same person as who was allowed to view the particular field, right? So the field thing just carries over. The interesting thing is, what is the invariant that holds for this subquery? And that invariant is essentially, and this is where this representation or the semantic of that particular field comes in. Essentially, the invariant is some predicate, is any predicate, if you wish, such that the representation implies that predicate. Okay, so the representation R of V implies the invariant on R. Okay, and this is how at the type level we can kind of track the semantics of the SQL query as you build them up with this equals or and so on. There's the AND operator. Okay, look at the AND operator. So here what it says is, if you have two subqueries, query 1 and query 2, with policy 1, invariant 1, policy 2, invariant 2, the resulting query, its policy is going to be given by the conjunction. So again, you are the people who are allowed to view the left query and the people who are allowed to view the right query. So the intersection of those two. And furthermore, the invariant is also going to be the conjunction of the two invariants. Okay, so you can conjoin the sub invariants. Similarly, you can take the disjunction and so on and so forth. Okay, the last bit is, how do you actually extract the queries?
Do you allow complementation in policy, or only and this one? Do you allow complementation policy?
We do not allow complementations in policies. I mean, we allow them at a primitive level. In the case of, for example, instead of equal, you could have not equals.
But not at the policy level.
Right, not at the top level. Right, that would cause all sorts of. Okay, sorry. The last bit is, okay, now that you have you have the query and the invariant associated with, you have the policy and the invariant associated with each query. Finally, when you execute a select and project, what do I know about the results? Okay. So here, let me show you what the select API looks like. And what it says, there's the plain API. It says that if you have a query who is supposed to return a collection of rows from some table, according to of type row, then the execution is going to be a computation that returns a collection of rows, right? When you run it. We are going to give it a more refined type that says that if the query had some policy and some invariant, then when you execute the select, the set of authorizees is given by auth, which is different than Paul. We'll see why in a second. And of course, there are no observers because right now we're not sending any data out. But there's a very subtle relationship between auth and policy and invariant. And here's what that is. Okay, it's captured by something we call a view policy, which says, this is what it is in English. The invariant rows authorizees must satisfy the policy. Okay, so we don't require that all the rows that policy and invariant don't hold for every row. We just require that if R is a row that satisfies the invariant, then the authorizees must satisfy the policy for that particular row. Okay. And this is a kind of a weird thing. So remember, we don't want the policy to hold for all rows, only the rows returned by the SQL query. Because if you think of, for example, the one where we did the public, where we checked if the level was public, again, as Sanjeeva said, if you did it kind of directly, you would say, hey, you check for user ID and the policy says only user ID can see it, but not really. We just want to check that the policy holds only for those rows that are returned by this particular query. And this query guarantees that every row that is returned to you is going to be marked public. Okay. And so here's a concrete example. If your query has the type own and level R equals public, okay, so it's authorizees are own. So it says only the user can view it unless the level is marked public. And the invariant is that the level is public. Then when you run select query, in fact, the results are viewable by everybody. Why is that? Because the following implication holds. It's the same implication we had before. Level R equals public, which is the invariant, and true, this is the authorizees, implies this particular policy over here, implies own. Okay. And this is why we need to actually connect the query semantics. Otherwise, everything would just fall apart. Everything would be far too weak. Okay, that's pretty much it. These are all the difficult bits. If I have a few minutes, Deepak, I will tell you a bit about the evaluation, but I'm happy to also stop now if people want to leave.
Yeah, I think you go ahead, Ranjit. Yeah.
Okay, thank you very much, Deepak. Very kind. Okay, so we built all this stuff, and now does it actually? How useful is it, right? So we did three kinds of evaluation, if you wish. One, does it capture interesting policies? Two, how much extra work is it to use this particular approach? And three, I set out with this claim that, oh, it shrinks the kind of code that you have to trust. Does it actually do that? Okay, so let's look at these one by one. Does it capture interesting policies? So what we did is we looked at I think 4 different previous frameworks that aim to do this kind of thing. Orflow is a static framework, and Jacqueline, Hales, and LWeb are both dynamic frameworks. Which as Professor Shamsundar said, they use this label style. Actually, Jacqueline doesn't use. Hales and LWeb use this labeled IO, and Jacqueline has used something called faceted computation, right? So they have these, various different case studies from all of these with various kinds of security policies. And it turns out that all of these port over very nicely into our framework without any difficulty. Orflow is static, but does not actually do full IFC, information flow control. So you can miss the kind of implicit flows that, who was it that referred to with some, right? These guys, Jacqueline, Hales, and LWeb are all dynamic, which means that policies are very, very expressive because you can just make up, whatever predicates you like and whatever labels you like and check them at runtime. But of course, the checking is late and they impose a runtime overhead. And so the nice thing is that Storm essentially lets you support all of these policies, except for one, I should point out. So one doesn't mean all of conference. Even within conference, there were 20 different requirements. One of those 20 we could not support. And that required, since our thing is sort of tethered to this SQL thing, the policy required certain rows being missing from the database. So it's kind of related to what Professor Shamsundar said about negations in your queries, right? This is slightly cumbersome because all our thing works with all the information has to be present in a kind of positive, constructive way. It's hard to write policies on things that are absent from the database row. Okay, how much work is really needed? So what I sort of alluded to, but I didn't, the price of compositionality is that for some server actions, yes.
Sorry, Ranjit, I think I missed it. What do the columns mean? Model and policies?
Oh, sorry. So benchmark is benchmark. Model is just the database description. So if you go back to this, how I said it has a field called user with the user's name and the user ID and wish, which has this, that, and so that's the model. That's what is called model in this world. So just a description of what the database schema is. So what this is describing is how big was the database description schema without any policy at all, just the database description schema. And this is the extra lines of code for specifying the policies. Does that make sense?
Sure. And I guess somewhere you're going to talk about the size of the code and stuff.
Yes, correct. Yes, it's just coming up right now. Okay. So how much extra work? So the price of compositionality is that you often have to write sort of type signatures for these monadic actions, right? For these computations. So let's say, oh, here's a server function and you want to specify who its authorizees and observers are, for example. So if you have a conference management thing, you might have a function called get authors, and you would say, okay, for any, it takes as input a paper P, and the computation, it doesn't send any data out. So the output is none, but the set of users who are allowed access is something or the other, right? So these are not trusted. They are just to make the type checking work out in a local fashion. But nevertheless, you have to write this to make the type checker sort of check the body of this code, right? It's a kind of modular analysis. And so the natural question is how much you have to write and how big is that compared to the code you have to write, right? So this is your question, I think, Saurabh. So I had this as a table, but I thought I'd turn it into a graph. I mean, roughly speaking, so we built these. So these three are from the previous benchmarks, conference, course, and wishlist. And these are two new applications that are sort of end-to-end applications I'll describe in a second. So, I mean, long story short, it's about 1 line of type annotation per about 20 lines of code. And in this case, I think the largest of these has maybe 750 to whatever 900 odd lines of code in the server, right? So just the controller code, setting aside the client, right? So does this answer your question, Saurabh? Roughly speaking, this is the kind of, the blue bit is just raw code.
And so I thought you were doing a centralized policy, right? I mean, I thought you were kind of getting rid of the type annotation. So I'm a little lost, but maybe.
So, okay, that's a very important point. The policy itself is centralized, but you need these extra annotations on the code just to make the, think of these as, these are type annotations to make the code type check.
Okay, these are like,
how should I explain?
Okay.
Like think as loop invariant. That's a perfect analogy. Somehow, how you have to write loop invariants, or in order to make your type, to make Daphne happy. Think of it as the equivalent.
Sure. So,
right?
so can you go back to the graph once again? Yeah, sure.
Yeah,
that makes sense. Thanks.
That's a great analogy. I must remember it. Okay. Yeah. So these annotations are like loop invariant annotations to make the thing happy.
So I guess you're saying that, you know, you were able to kind of do this for programs as big as like 1,000 lines of code.
Correct.
1,000 lines of Haskell code. I see. But I mean, like,
correct.
I mean, is scalability an issue? I'm guessing it should be, right? Or it's not.
Well, you know, the thing is, I mean, in a way, yes, it is, but no, it isn't, because the checking is all modular, you know, so you could have, like, if this was 2,000 lines, it would kind of scale in a linear fashion, because ultimately you're just checking one procedure at a time, right? That's what the purpose of these little annotations is. Does that make sense?
So Ranjit, is it loop invariance the better analogy, or the input output specifications on a function a better analogy?
Actually, I mean, the loop invariants are the better analogy here, because think of it, they're not, you know, they're not strict. They're the better analogy because with functions pre and post conditions, I think of function pre and post conditions as the specification I want to have checked. As opposed to
something that helps you to get to patch things together. Okay.
Exactly. While here, these are not trusted. You see what I'm saying?
Right.
Like you just need something that type checks and any damn thing will work. The only thing you really have to trust is the policy.
It's more like assertions that make your proof easier to do.
Correct. Think of it as assertions that make them correct. But they're in this kind of what I would call ergonomic form factor, which is just function signatures, right? Which, which makes things modular, etc.
I guess they involve some kind of logical predicates and stuff, right? And I guess the programmers will know these kind of things. So, I mean, do you think this is a problem? And if so, do you think there's a way to do this automatically in future, or what do you think? I mean,
I think there's, you know, to write those specs, you mean? To write these annotations?
To do the annotations,
I think it, you know, the short answer is it's not really that big of a problem. But that being said, it's right now the only people who've written them are the authors of the system. So sure, we don't think it's a problem, but I'm sure it's going to be a problem if you have, you know, if you have other people trying to use it, right? So I do think it is a bit of a problem. I think in principle, it should be possible to synthesize a lot of these. We have not thought very hard about that particular problem just because it was easy enough to just like, you know, a lot of these are, you kind of, oh, you know what this get authors is supposed to do. And you kind of know it kind of matches something in the policy and you're like, oh yeah, that's what this function is, and you drop it in, right? So a lot of it is kind of boilerplate. But in principle, it should be possible to synthesize a lot of this, in my opinion.
Okay.
Yeah.
Ranjit, one question. So these annotations are in addition to writing the type signatures for the operators.
The type signatures for the operators are set in stone inside the framework, right? So you, as a user of the system, you don't write those. So we wrote those. We have died for those sins, and so you don't have to do that. Those would be impossible to write for an ordinary person. They require a very, very, very clever graduate student to figure out. So the things with those bounds. Because in a sense, all of this work is the type signatures. That is really that, oh, you can take all of this and just model it all in the type signatures. We didn't build the tool. The tool existed already. We just came up with the type signatures, and it took us many years to do so. But yeah, those type signatures are in the library, and thankfully you don't have to write those. You have to write these, which are much simpler and kind of roughly model what the code is doing. I should also point out that half of these are of the form true and false. You write action, true, false, action, true, false. So I mean, there are no observers, or all the observers are true. So they're literally trivial. They're top and bottom in the lattice that Sanjeeva was referring to, right? So we have some fairly detailed counts in the paper. So I think maybe a half of them are non-trivial in that they're, the predicate is not just true or false. And in that case, they sort of quite closely match something that's in the, what you're supposed to be doing. Okay, and finally, this business of, what is the policy? What do you really have to trust, right? So we built these two web apps. I have these little videos that explain them, but maybe I'll skip that. So the server is written in Storm, right? And the front end, which is what the client sort of interacts with, that's written in JavaScript using a very nice framework called Vue.js, by the way, which I heartily recommend if you're in this business. So there's one of them is a kind of virtual hallway track type thing, which we've used at a couple of workshops at PLDI and at CAV with about 100 odd users. And you have different rooms, like, you can name the rooms and you can see who is in what room, and you can go and join the room. So there's a little video, but maybe in the interest of time and to spare myself some embarrassment, I'll skip the little video. Oh gosh, I can't seem to skip it. You can see somebody goes and joins, and there's this person, this is my student. I've been waiting to tell you, I just saw this amazing movie, Godzilla v. Kong. Have you seen it? It just has amazing effects, and that's kind of a given these days. But even I'll skip it across, and then he can kind of go across and maybe join. There's Nico. He goes to another room. You get the idea, right? Oh, hey, Nico. And then this is another app that we wrote, which I quite like. Actually, I use it a lot myself, where the idea is that you're doing in-class group programming exercises. And so as the instructor, I want to see what all the groups are doing. And each group has their own text pane, and they can edit their stuff. So there's like 4 or 5 students or whatever in the group, and they're writing their own code. So they have a shared buffer within themselves. And I can kind of see what's going on inside all the buffers, right? I have a bird's eye view to see what kinds of mistakes people are making. And so we've been using this for a couple of years now with about, classes of 50 to a couple of 100 odd students. There is a video for this, but I might just skip that apparently I can't figure it out. Right. I think you get the idea. Somebody goes and types stuff over there, and public, static, etc., etc. And then this is the student view. And then as you can turn and become the instructor, and the instructor can see all the different views, right? Okay, very well. And does Storm reduce the code? So same thing, by the way, Saurav. So here the server is like 756 lines, 700, 800 odd lines. This is the data description. So the database schema is about whatever, 30, 40 odd lines for these two, with users and tables and groups and whatnot, right? Rooms, what have you. The policy is about that same size. The client is, as you might imagine, really where a bulk of the work went. And so the long story short is that the policy code is, what is it, like 4% of the server. And if you look at the entire app, it's, it's like under 1%, right? Okay, that's pretty much it. That's all I want to tell you about. If you want to learn more, it's all over here. There's a paper that describes all of this stuff. If you want to play with the system, it's all over there. And let me stop here. And thank you all for giving me the extra time. Thank you very much.
May I ask you some questions? Couple of questions.
Of course. Yes.
So auditable, is it related to provenance, or what is the thing?
By auditable, we are using it in a very vague and informal manner over here. We really just mean it's not scattered across your entire code. It is super centralized in one place. And that's it. There's no, beyond
it is
that,
not
no
the
technical
database provenance or anything of that nature.
No.
Yeah, you know, one thing I was quite curious in the web applications, do you get non-terminating and also time-sensitive queries? And if that is so, then there is always a problem of leak, like in the language security.
That's a good point. That's a very good point. So here, I mean, I guess now that you mention it, I mean, by default, the way by the way all of this works, I did not make this explicit in the talk, it occurs to me, is that the way all of this works is using a tool called Liquid Haskell, which is the refinement type checker. And as I said, the framework, quote unquote, is, I mean, of course, we have the implementation of the database and this, that, and the other. These monadic, but it's really the type signatures, right? And so on. Now, by default, Liquid Haskell also checks non-termination. It checks termination. It checks that everything you write is terminating. And so in this particular case, for all the benchmarks that we looked at, everything terminating. But you're right. I mean, in general, we have not.
Because if you use some kind of a public and a private, you can do some time-sensitive operations to see some information can get leaked, the kind of a thing or the other. So, and one or two more questions. You know, you have only R and N. It is similar to something like Mitchell used to get some kind of an algebra for the DIFC kind of a thing or the other. And so, in fact, in our conversation, the collaborator of Mitchell asked me, whether do you need any negation at all for the things what he was looking for in a language theoretic sense of the reader or writer. I didn't know. And I'm not very clear about that kind of a thing. Maybe the last question, do you need declassification at all in the web server applications?
I was waiting. We always get asked this. So, the short answer is, in theory, I'm sure we need some declassification somewhere, but in practice, we have not found a need for it. And my conjecture is,
for example, if you take the database example, or the hot CRP or the hot crack, you need declassification, because the chairman has to technically declassify so that it becomes available to everyone or the other. And so, in fact, that is where I think the Liskov had used a database with a row-wise policy kind of a thing, for which we said from our reader-writer model, we can go for a cell-based thing, and then you can really capture the declassification in a real non-discrete manner kind of a thing or the other. From a lattice theoretic perspective.
I had this question too, Shyam, and I had this wanted to ask Ranjit about, he's cooked up the storm, but how does it deal with Liskov and Schultz's stuff when they were talking about databases where they were doing it at the granularity of rows, but you're able to do it at the granularity of a field, the policy.
No, in fact, I think, Sanjeeva, I think the granularity of a cell was already shown long back by Denning, Dorothy Denning.
Yes, of course.
Yeah. And so that is not an issue, which shows anyway, it gives a much better refinement kind of a thing. But what Barbara Liskov did was essentially from a declassification perspective.
With Andrew that she did this.
Yeah.
So here's the thing. My sense, and it is entirely possible that the answer I'm giving you is hopelessly naive over here. But my sense is that a lot of these problems with declassification came about because these earlier systems were using sort of these label-based mechanisms and far simpler type systems where your policies could not refer to the values themselves. In our setting, for example,
Ranjit, that was why I asked you about the dependent types.
Yes.
And
here, this program chair example that Shyam mentioned, we would just literally have a bit somewhere in the database that says, status is like done, or whatever the PC decisions are made. And now you can just use that in your policy. Did you check?
No, another example I can give you, Ranjit, is an auction. In fact, I think in the DIFC, Andrews uses that find that an example, but there he has problems. And that is where you need the declassification. If without declassification, you cannot ensure the complete property of the auctioning.
No, I think all of that. I don't have a I agree. Statement. Yeah. It's just Andrew's type systems were far weaker than the kind of thing we are allowed.
Yeah. The other thing probably Shyam and Ranjit is that in all these auctions and conference review system, there's a temporal aspect which is sort of being glossed over in the example.
Very good. Yes.
Because they have to fit them into a paper, but I think you really do need a temporal logic sitting outside this and saying, this holds until that set of policies.
Correct. I agree.
Yeah. So Ranjit, great talk. I was just curious about why you thought that first of all, I must say that I hated the word authorizees, which I would just use authorized. But why? What did you think was the hardest part of the eureka moment there? I mean, you seem to suggest it was observers is contained in the authorized. That seems
no, that was not. I mean, so there were two eureka moments for me. But remember, this is work done with a whole bunch of people, right? With Nadia, who actually came up with the authorizee observer inside the refinement types thing, right? In an earlier paper. And so Nadia and friends knew that stuff for like 5 years. It's a funny thing. They had this paper, it's been kicking around for 5 years, rejected constantly, and then it won the best paper award. But anyway, she knew this thing for 5 years, right? This authorizee observer thing. And she was like, so that bit we knew, but I didn't know it. So I mean, I started thinking about this in like 2010, this general business of web frameworks and doing IFC. And I remember a conversation with actually Andrew Gordon, if you know Andrew, and he was also thinking about it. He was like, but how do we do it as refinements? There's this kind of, the way the implications work is backwards. With integrity policies, and we were kind of foxed by this, and we kind of gave up. And so anyway, Nadia solved that problem, right? You stick it inside a monad, and then you use this, these two labels, and anyway, that was all great. But even after that, we sort of struggled for a long time with figuring out how to capture these SQL semantics inside the refinements. That was because the point is, if you want to put it make it as a framework, you have to be able to represent all the query operators like equals and or whatnot, right? Select using, in a way that's agnostic to any particular application, right? It has to be completely generic. And so that we really struggled with, like, how are we going to encode this SQL semantics? And there was this student, Rose, who really cracked that. We were sort of going around in circles. And anyway, when Rose figured that out, that's how that's how these two bits kind of connected. And now it seems kind of straightforward, but it took us a long time to somehow connect that.
For me, the eureka was using the uninterpreted functions P and Q for the compose.
So that's you're right. So I mean, in a sense, that is what Rose figured out, right? Wait a minute, everyone, you can use that trick over there So there was a bunch of Okay,
great talk. I've got to run, but we'll
thank you, Ranjit. Thank you.
Thank you, Sanjeeva. Thanks, Shyam. There's a couple of questions on the chat. Should I attempt to answer them? Yeah,
you can go ahead and answer them.
JIT people over here. So long story short is there's no performance overhead as such, because there's no runtime checking of any kind, right? It's just whatever your code is running. So most of these are checks, you have to do some run, these are just queries. It's just the native code that's running, right? There's no extra anything that's being tracked. How much of a benefit does laziness provide in embedding the policies? I don't think we are using laziness at all. I mean, it's a kind of, it's there, but we're not really using it in any way. Because the policy is just this kind of orthogonal predicate. Again, it's not run, right? This code is not being executed in any fashion. So all of these policies are just compile time kind of entities, if you wish. They're entirely erased from the execution. So we don't really use laziness. How does SQL query optimization? Now, that's a very good question. I mean, we are assuming that whatever queries you execute in the code, whatever queries you sort of issue from the code, right? You can think of your server code as dynamically generating SQL queries that are then executed. We're assuming that the SQL queries, they preserve the same semantic. So I don't know if there's some weird way where SQL can do some trickery which somehow ends up executing different code than what.
Yeah, for instance, if it decides to do the project first, and maybe at that point ignores your, I don't know. I don't know if there is.
That probably won't matter as long as ultimately the collection of records that's returned is the same as, you know, what was described in the programs type. You know what I'm saying? It's fine to reorder things. That's because those are not going to be observable to the program. The only thing that's observed, of course, we're not doing any running time measurements. So there's like a timing insensitive kind of thing, right? Right. So that might make a difference. But I will say there is one important thing that you have raised. So on the one hand, I was blithely saying, oh, there's no performance overhead. Checking is at compile time. This is true. But remember, you have to be able to restructure your code so that you only use those SQL operators that we have figured out the types for. So now this is not an entirely academic limitation. Often in this kind of web app type of setting, you want to write these queries which, are what database people will call nested joins. Okay. And for nested joins, the naive way, you can write them as essentially a sequence of iterated select queries. Now, of course, if you write it as a set of sequence, it's easier for the type checker if it's a sequence of selects because we know how to type select and that's great. But that's much slower than writing it as a nested join directly, right? And so in a sense, the work here is for the framework authors is how much of SQL can you support? Can you write sort of nice types for? And so in an earlier version, we did not support join. And so you had to write these nested selects, which was dog slow. It's like, that's a well-known, I think they call it the N+1 problem in the sort of database literature. But then we sort of figured out, oh, wait a minute, here you can just write a type. You can actually encode join directly. And then you can restructure your code so that it directly uses joins. And that's much faster without compromising security. Does that make sense?
Yeah, so that is sort of related to my first question also, because is there a way, because Haskell is lazy, maybe even if you do a sequence of selects, it won't trigger it at the very beginning. Maybe there is
a good point.
Maybe
that's
there is
a good point.
So that is why you can actually view it as some eager selects and so on with the policies, but Haskell will sort of do the optimization for you in some sense.
Correct. You're right. And in fact, this is like this, this link work, LINQ, language integrated queries, which this was like Eric Meyer in like 2005. So this was like a really cool, and it was a really big deal. In a sense, Link was like one of the pioneering ORMs in this style, where Eric Meyer basically showed, wait a minute, if you think of this act of building database queries as a kind of monadic computation, where where you separate the building of the queries from the execution of the queries, then you can build up this kind of query pipeline, and then you can say, okay, now execute. Right. And at that point, you have a complete knowledge of the structure of the query, and you can start playing all kinds of clever optimizations on that query, right? And then these people at Google built this Flume Java. Anyway, this has been a big deal, right? This is Dryad Link and TensorFlow. All of them, they start with this kind of central insight. But yeah, you have a good point. I think you could perhaps do something like that. Right now, the kind of ORMs that we're using just directly issue the queries, but I think you could be cleverer, where you somehow exploit this laziness and say, okay, you don't really want the data till now. And so let me optimize your query a little bit, even if you wrote the double.
And I suppose relatedly, even if you want to do some sum or something, you do it at the Haskell and not as an SQL query, because maybe when it actually issue the query, you can do it as a SQL maybe, but in your code, you are just your type annotation and your the propagating all those levels, etc., becomes much simpler, I suppose.
Correct.
You only have very few SQL operators.
Correct. So it's a narrow interface.
Maybe anybody else has any questions in the audience?
Thank you, Ranjit.
Thank you. Okay. I think we're out of questions. Very good.
Okay. Actually, Ranjit, I have one quick question.
Oh, yes. Yeah.
So so have you all, so I guess this is a conservative way of checking, right? I mean, you may throw out some programs, say that they don't meet the policy.
Correct. Right.
So, I mean, have you evaluated your tool in that respect? I mean, are you too conservative? How conservative are you? And, are you throwing away some good programs?
I mean, again, I guess in principle, We have not systematically, I mean, let me just say the only evaluation we have done is we sort of built these 4 or 5 apps, right? And in the course of building those apps, every time the type checker complained, it turned out there was some subtle issue with the policy, right? There was, there's a kind of, in the paper, we have this 1 or 2 paragraph description of somewhere where we thought, oh no, it was being conservative and it's rejecting this piece of code because of, how conservatively we set up the types. But then, my students they were like, they thought about it for a few more hours and they're like, no, actually it's not being conservative. There is this, issue where if you do this and then that happens, if there's this weird temporal ordering, then, you end up violating the policy. So again, the evidence is entirely anecdotal.
Right.
There's no systematic kind of
but
thing.
That's good enough. Yeah. That's a good sign. Okay, so yeah, thanks a lot, Ranjit. Excellent talk and very enlightening and entertaining at the same time.
Yeah, thank you very much, Deepak. This has been a real pleasure.
Yeah, and thanks especially for
Bye, everyone.
Waking up so early in the morning. And
well, I have to get up for my kids in any case. So